Hi everyone, so we're moving on to lesson 2, and today we're going to learn how we actually calculate heat. So in calculating my heat of reactions, Q is going to be my symbol for this heat. It's also equal to that delta H that we talked about on Tuesday. Okay, so Q is going to be equal to that delta H, and it's how we measure heat. It's going to be measured in joules or in kilojoules. So generally we do joules, but every once in a while you'll see it in kilojoules. So it's important that you know how to convert from joules to kilojoules, with joules being the base unit and kilojoules being my prefix there, my kilo. And you practice that a little bit in the review, but just so that you remember, if you're going from joules to kilojoules, you divide by 1,000. From kilojoules to joules, you multiply by 1,000. So if Q is a positive number, my heat's going to be endothermic. If it's a negative number, my heat's going to be exothermic. And the heat of a reaction is going to be based on a couple of different things. The mass of the substance, for one, the temperature change that it undergoes, and the specific heat of a substance. So the specific heat capacity of a substance is the heat needed to raise the temperature of 1 gram of that substance by 1 degree Celsius. So we have a couple of examples here on different things and their specific heat capacities. You'll notice these metals, so like aluminum, copper, gold, they have really low specific heat capacities. It doesn't take a lot of heat energy to change their temperature by 1 degree Celsius. But something like water has a specific heat capacity of 4.18. That's considered a very, very high specific heat capacity. So it's a little bit more challenging. You have to add a little bit more energy to change the temperature of water by 1 degree Celsius. And this makes sense if we think about it. Okay, the ocean, we know, tends to stay around the same temperature. Even though that sun is beating down on it in the summer, it takes a long time for that temperature to go up. When you go in the ocean at the beginning of the summer, it still feels really, really, really cold. Where if you've got like a metal bench outside at a park and you go to sit on it in the hot summer sun, it's going to burn you. It's going to feel really, really hot because it has a very low specific heat capacity. So the specific heat capacity is on our reference tables for water specifically. So if you look at table B says physical constants for water. So when we look at this, we see 3 different numbers. The one that we're interested in right now is the last number. We'll come back to the other two, but we're looking at the specific heat capacity of H2O specifically in the liquid phase. Now, things do have different specific heat capacities depending on their phase of matter. For what we're doing right now, we're only looking at the liquid phase. When we get further along, we'll look at different phases of water. But the specific heat capacity for water in the liquid phase is this 4.18 joules per gram times Kelvin. Now that can also be replaced with joules per gram degree Celsius. You can use those units interchangeably here. So if I want to calculate my heat when I'm looking at a temperature change, I'm going to use this equation right here. This Q, which is my heat, is equal to M, which is my mass, times C, which is the specific heat capacity, times this delta T. And hopefully we all remember that this triangle means a delta, and that means the change. And generally I'm doing final temperature minus initial temperature here, and that's what's giving me my my change in temperature. This equation is located on table T on your reference tables. It's on the back of your reference tables, so it's not something that you need to memorize. And all of these variables are also laid out on the back of the reference table. So if I want to solve for Q, for example, I have this question right here. How much heat is needed to raise the temperature of 500 grams of water by 15 degrees Celsius? My first step is I'm going to list all my known variables. So I know that I'm using Q equals MC delta T here. So I'm going to look in my question, figure out what variables I know. Okay, so I'm looking for Q, I'm looking for M, I'm looking for C, and I'm looking for delta T. So my Q is my heat, and I see here it says how much heat. So my Q is my X. Okay, my M is my mass, so I'm looking for something in my problem that says grams, and I see it right here. It says 500 grams, so my mass is 500. My C is the specific heat capacity. And I don't see that in my problem, but I see that we're talking about water, which means I'm going to use the specific heat capacity that's listed on table B. And that was 4.18 joules per gram degree Celsius. Then my delta T is the change in temperature. It says I'm changing it by 15 degrees Celsius. So my delta T is 15. So now that I have my known variables, I'm going to plug them into my equation and determine my product. So I know that it's Q equals MC delta T. My Q is my X. My mass is 500. My C is 4.18. And my delta T is 15. So to solve for my x here, I take 500 times 4.18 times 15. And when I do that, I should get 31350. Hopefully we all remember the last step is to check for sig figs. So I want 2 sig figs in this answer because this 15 degrees Celsius has 2 sig figs. So I take my first 2 sig figs and the others become zeros here. So I would have 31,000. And then my unit for Q is going to be this J, and this J stands for joules here. So this is 31,000 joules. I can also do these types of problems solving for a different variable. Let's say that I want to solve for the specific heat capacity. Okay, and this problem says the temperature of 95.4 grams of copper increases from 25 to 48 degrees Celsius and absorbed 849 joules. Calculate copper's specific heat. And so I know I'm going to be using that same equation, that Q equals MC delta T, because we're talking about heat here. So I want to list out my variables that I know. My Q is my heat, and remember Q is measured in joules, so I'm looking in the problem for something that says joules. And this right here says joules, so my Q is 849 joules. My mass, measured in grams, I'm looking for something that says grams, it's right here, so it's 95.4 grams. My C is my specific heat, and I look and it says calculate copper specific heat. So that's my X. And then my delta T is always the final temperature minus the initial temperature. So I see my final temperature is 48 degrees Celsius. My initial is 25. So my delta T is 48 minus 25, which gives me 23. Now I plug everything into that equation. My Q equals MC delta T. So my Q is 849. Okay, it's equal to my mass, which is 95.4, times my specific heat, which is X, times my change in temperature, which is 23. Okay, so I take 95.4 times 23, divide that into 849 to isolate my X. Okay, and this should come out to 0.39. Again, I check my sig figs. I want 2 sig figs because those temperatures have 2 sig figs. Then my unit here, my unit for specific heat is going to be joules per either grams times Kelvin or grams times degrees Celsius. And if you forget that unit, you can look on table B where the specific heat of water is listed. The reason that I couldn't use that number for this problem is I wasn't talking about water. That 4.18 is only for water. Here I'm talking about copper. That's why I was solving for the specific heat. So hopefully we see that this is really just a plug and chug equation. It's not that terrible. Okay, so you've got example here. Take a second, try to solve it. All right, let's walk through it. Okay, so again, I'm going to be using that Q equals MC delta T. I'm going to list out my variables. My Q is my heat measured in joules. It says how many joules of heat. So that's my X. My M is my mass measured in grams. Right here, it's 50. My C is my specific heat. Okay, I can use that 4.18 number because we're talking about water here. So I'm going to use 4.18. And then my delta T is my change in temperature. Okay, so it's final, which is 58.6, minus initial, which is 30.2. When I take that 58.6 minus 38.2, I should get 28.4. And then I plug my numbers in. So X equals 50 times 4.18 times 28.4. So I multiply all those together. It should have given me 5935.6. But I need to check my sig figs. I want 3 sig figs in this answer. So I should have, sorry about that, 5940, and then my Q is heat, and that's going to be measured in joules. So a J there, 5940J. Okay, take a second and try this one. All right, so very similar here. Again, I'm going to be using Q equals MC delta T. I'm going to list out my variables. So Q is heat, and it says how much heat. So that's my X. M is mass. That would be 25 grams. C, it's water, so I can use 4.18. And my delta T, I take my final, which is 47, minus my initial, which is 27, gives me 20. So I have X equals 25 times 4.18 times 20. Multiply those together, it should come out to 2090. I check for my sig figs, I only want 2, so I take the first 2, and that should give me 2100, and my unit is joules. All right, give this one a shot. All right, so again, same equation. Q equals MC delta T. My Q is my heat. It says how much heat, so that's X. M is my mass, which is 100 grams. C, it's water, so I can use 4.18. And my delta T, it's telling me it's changing by 50 degrees Celsius. So my delta T is 50. So I take X equals 100 times 4.18 times 50. Plug it in, and it should get me 20900. Okay, I only want one sig fig here because this 100 only has one sig fig. So that should give me 20,000. And my unit for Q is joules. So 20,000 joules. And last one, give this one a try. All right, so still using that Q equals MC delta T equation here. My Q they give me this time, Q is in joules, so that 900 joules is my Q. M is my mass, and it says calculate the mass, so M is my X. C is the specific heat. I'm not using water here, I'm using aluminum, and it tells me the specific heat is this 0.902, so I can't use the 4.18 number because I'm not dealing with water here. And then delta T, I take my final temperature, which is 38, minus my initial, which is 30, gives me 8. So I have 900 equals X times 0.902 times 8. So I take 0.902 times 8, divide that into 900, and it should give me 124.7. But I only want one sig fig here because that 900 joules only has one sig fig. So that should give me just 100, and it's mass, so my unit is grams. All right, so that's it on this lesson. Should have been hopefully a nice, easy lesson. We're going to come back to calorimetry next week because that's going to be a little bit more complicated. So we'll come back to calorimetry next week, and then we'll start in on the next lesson from there.